Okay, good afternoon, everyone. We are going to finish 3.3 today. We didn't quite get it done last time. We're going to start 3.7, and then we won't finish it today. We'll have to finish that next week. So that's our plan. Do you have any questions before I begin? Everybody's okay? Are you sure? Okay, then let's do a quiz. All right, so I'm gonna put up a poll. You have two questions here, A, B, C, or D for each one of them. I give you a function. I ask you to find the derivative. Sorry, it looks a little sloppy. My little digital pen was broken today, so I had to replace the tip. So it looks a little wonky, but I think you can make out what it is there. Okay, good luck. Let me put the poll up. There's the poll. Okay, see what you can do in like 6 minutes. You can use your notes and stuff on your formula sheets, whatever you need. On these answers, I've done just a little bit of simplification, just a little bit. So nothing drastic, but I have simplified some of the answers just a slight bit. Minute and a half left. Hey everyone, I got a phone call. Sorry. Hang tight. Okay, sorry about that. Although you probably didn't mind. All right, so let's go through this. On the first one, so let me start with this. What were the main ideas that we took away from last class? Here they are. First of all, if you're ever going to take the derivative of any number a raised to something, I'm just going to call it like a yellow box, okay? If we want to take the derivative of this, then what you're going to have to do is write a to that same whatever's up there times natural log of a, and then multiply that times the derivative of whatever was up in the exponent. Okay, so you basically like rewrite the exact same expression, put natural log of a, and then you have to take derivative of what was up here. Now, in the event that that a is e, which is the very special case, then the only difference is that you still do e raised to that box, but you don't need to put natural log of e because that turns into a 1. So we just don't even do this. And then we multiply that times the derivative of what was up in the box. Okay. Then we start talking about logs. So when it comes to logs, we have different derivative. If you do log base A of some box, and you want to take the derivative, right? Then it'll be 1 divided by whatever was in that box, whatever's in the log, times natural log of A in the denominator with the box, and then times chain rule the derivative of what was in the box. And then if we have the natural log, instead of log base A, just the natural log of a box, then when we take the derivative of that, that's just 1 over whatever the box was times the derivative of what was in the box. That was kind of like the main takeaway in terms of derivatives from last class. So on this quiz, on the first one, we have essentially natural log of a box, right? So the derivative of that would be 1 over the box, right? 1 divided by the box. So it can't be this one or this one, right? So it's either this one or this one. And then you're supposed to say times the derivative of the box, but that's a product. So you have to run the product rule. So you take the derivative of x, which is 1, times sine x, this one, plus now the derivative of sine x, which is cosine x, and then times x. So it's this one right here. A, I think if you chose A, then what you might have done is forgot the product rule and just took the derivative of x and put 1 and took derivative of sine and put cosine. But that's not right because that's not product rule. So the answer here was B. Now on number 2, we have this one right here, this top one. We have A raised to a box. So the derivative of this should be itself, which means it's got to be the first one or the second one. Can't be this or this. And then we have to put the natural log of 2, right? That natural log of A has to be there. So I need natural log of 2 here. So already you can tell it's got to be this one. And then you have to put the derivative of what's up here, right? The box, you have to take derivative of that. Again, that's product rule. Derivative of x is 1 times natural log x plus the derivative of natural log of x is 1 over x times x itself. And that these x's reduce out, and that's where you get that 1 from. So the correct answer on this one was B. So let's see, how'd y'all do? 90% of you got B on the first one, and 60% of you got B on the second one. Any questions? Any questions? No? It looks like on B, or sorry, on number 2, a lot of people put the A and just forgot the natural log 2 has to be there. So just be careful whenever your base, whenever the base here is something other than E, you've got to put that natural log of A in there. Okay, let's move on. We're ready to move on? Yes, yes. Okay, so I wanted to remind you of a couple of properties of logarithms that I talked about when we were talking about logs last class. And I told you this was something from college algebra where you do this thing called expanding and condensing logs. It's a way to take a complicated log expression and rewrite it in kind of easier and like an easier form. And these are the 3 properties. And I'm about to use them to do a problem where I'm going to try and take a derivative of something that looks really, really bad. Okay, so take a look at this right here. Y equals natural log of, let's say, the square root of x squared plus 4 over, let's go with x to the 5th plus x, all of that to the 7th power. So I want us to find the derivative of this. Okay. So you could do exactly what we've been doing, which is say, okay, I've got log of a box, right? Got log of a box. So when I take derivative of natural log of a box, I'm going to do 1 over the box, and then I have to take the derivative of this box, right? But do you really feel like taking the derivative of this box? I mean, look at this. This is a quotient rule that has some chain rule in both the numerator and denominator. It's a very complicated looking expression, right? So maybe there's a way we can use properties of logs to help simplify this problem before we take the derivative. So I'm going to try, and I'm not going to get y prime yet. I'm just going to try and rewrite this. Okay, I'm going to rewrite this. Okay, using these properties. So first thing let's notice is that the second property says if you've got something on the top, you have a logarithm, and then you have a fraction in the logarithm, right? Something yellow on top and something blue on the bottom. Then it turns into two logs that are being subtracted, where you can put the yellow thing in the first log and then the blue thing in the second log. So I see that I have a yellow thing on top and I have a blue thing on the bottom. And so I can use that property. That's what I'm going to do first. So y can be rewritten as two logs. It's going to be log of something minus the natural log of something else. Now, in the first one, it's the square root of x squared plus 4. And in the second one, it'll be the x to the 5th plus x to the 7th. Is that okay? I'm not doing any derivatives right now, right? I'm just rewriting the problem. That's all. Okay, now what else can I do? Well, I noticed that, or I remember that when you say the square root of something, you really mean you're raising it to the 1/2 power. So I'm going to rewrite this as x squared plus 4 to the 1/2 power there, right? That's really what that means. And then over here, minus natural log, and then I have the x to the 5th plus x, and then that's raised to the 7th power. Now I'm kind of highlighting the 7 and the 1/2 in red, because I want you to see this property here, the third property, right? It says if you've got something raised to a power r, that r can come out front and just sit in front of the log. So powers can come down. So what that means is I can take this 1/2 and bring it out here, and I can take that 7 and I can bring it out here and rewrite the log again. Or sorry, rewrite the equation, or the equation of y again. So I'll just have 1/2 sitting in front of natural log, and then inside I'll have x squared plus 4. And then minus 7 natural log of x to the 5th plus x. Questions there? So that's all just algebra. Okay, what I've done is I have expanded the expression using the properties of logs. So now when I think about this and think about the derivative, it's not as bad now, because when I do the derivative, just look at we have two terms, right? Two of these. So I can do those separately. They're separated by subtraction. So I can take the derivative of each one. And when I do the derivative of each one, let's talk about the first one here. The 1/2 will come for the ride, right? Because it's constant out in front. And if I try and take the derivative natural log of this box, that's going to be a lot easier for me to do than it was up here, right? I can do 1 over the box and then times the derivative of the box, but the derivative of the box is super clean, right? It's just 2x. So this is going to be a much easier derivative to do. And same with this one. I have another box over here. So when I take derivative of the natural log of that box, I get 1 over the box times the derivative of the box, which again is not a bad derivative. So I don't have to do any sort of chain. Well, I have a little chain rule, but I don't have to do any quotient rule, right? I don't have to worry about the square root anymore. The 7th power I don't have to worry about. So this is just a much easier form to work with. So I'm going to do the derivative now. 1/2 comes for the ride times, okay, I get 1 over the box times the derivative of the box, which is just 2x, minus 7, okay, times, now 1 over the box here times the derivative of what was inside. Now, when I take the derivative of what's in here, I'm going to have two terms, right? So that's why I'm using a parenthesis. Derivative of x to the 5th is 5x to the 4th, plus the derivative of x is 1. Going to clean it up. 1/2 of 2 goes away. So I just have an x on top, x squared plus 4. minus, let me see. I'll just put that 7 up top with the 5x to the 4th plus 1, and then put that all over x to the 5th plus x. So I just slid this on top, moved this up here, and that's my answer. Much, much, much better than doing it the other way. Are there any questions on what I did there? Why is this not, okay. Why is this not wanting to come with me?
Sir,
Yes, what?
so if there's a number in front of the log, it's again just a coefficient. It just comes along for the ride.
Mm-hmm. Yeah, because it's a constant in front of a function, right? Because natural log is a function. So it's just like sine or, you know, any other function. So it's just going to come for the ride.
Thank you.
Now, I want to really make sure you understand just how nice that was, okay? I'm going to go extremely fast through this, and I don't expect for you to like write this all down. But if I did not do that, what I just did, okay, this is what the derivative would look like if you don't do what I just did. I would have to do 1 over the box. Okay, 1 over the box times, now I need the derivative of the box, which is a quotient rule. So I have to take the derivative of the top, which is 1 over 2 square root of x squared plus 4 times the derivative of what's inside, which is 2x, times the bottom function, x to the 5th plus x to the 7th. Okay, done with the first part, minus derivative of the bottom, which is a chain rule. 7 comes out, x to the 5th times x raised to the 6th times the derivative of what's inside of here, which is 5x to the 4th plus 1, but then times the top function, which is the square root of x squared plus 4, but then all of that divided by the bottom, x to the 5th plus x to the 7th squared. That's the derivative of this if I don't use the expansion stuff. I'd say that's a much more complicated looking derivative, right? Believe it or not, these two are equal. Everything you see here, if you were to simplify it algebraically, which would be a nightmare, you would get this. All right, I'm not going to do it, but do you see the power of the expansion of the log in this case? How it can really help us? Yeah. There's a couple of problems in your homework that you might actually be able to go back now and do, like number 9. Number 9 in your homework, that problem can be redone with this method. Number 18 can be redone with this method. If you did 18, 18 wasn't assigned, was it? Okay, good. Good, good. All right, let's keep going. Let me move that up. Okay. All right, have a new one for you. Y equals, check this out, x to the 5th times x plus 4 to the 3rd times x minus 5 to the 8th over x plus 2 to the 4th times the square root of x minus 8. Yeah, that's good enough. I want us to find y prime. I want us to find y prime. I want the derivative of this. All right, let's just first take a step back and realize just how bad this is, right? If I was asking you to take derivative of this, you would say, oh, okay, well, I have a quotient, right? I have a quotient. I have something over something. So I'm going to have to do the quotient rule, right? And when you run the quotient rule, the first thing you have to do is take derivative of the top. Well, look at the top. It's 3 things multiplied together. How do you take derivative of 3 things multiplied together? Well, you have to do the product rule, but you have to, within that product rule, you're going to have another product rule because you have 3 things, not 2 things. I did one example of a triple product way earlier in this semester. But it's going to be ugly, right? It's going to be hard. It's going to be ugly. And that will just be the derivative of the top. Then I have to multiply times the bottom, and then subtract from that the derivative of the bottom, which would be another product rule with the chain rule in here. Shit, that sucks. Then times the top all over the bottom square. Do y'all agree that sucks? Yes, you don't want to do that, right? You don't want to do that. I don't want to do that either. But see, the thing is, we cannot use a log. Like, we can't use the properties of logs. Why? Well, this one had a logarithm in front, right? I mean, this one was log of this, and so we use the properties, right? But here, there's no log, right? There's no natural log out here. So I'm not able to use these, right? I'm not able to use these because there is no log. Got it? Right? I can't. So it appears that I'm stuck. It appears that I can't do this. Well, other than the hard way, which is going to be very long and tedious, and I'm probably going to make a mistake. Okay. So this brings us to the last part of this section, which is a new way of taking derivatives when you have very complicated expressions like the one we're looking at right here. It is called logarithmic differentiation. Very, very powerful method. Okay, we can use properties of logs to aid us in finding derivatives. This method is called logarithmic differentiation, and here are the steps. The first step is you're going to take the natural log of both sides of the equation. So remember, I'm working with an equation here, right? Y equals this. So I'm going to take the natural log on both sides. Now, when it comes to the natural log and equations, you are always free to apply the natural log to both sides of an equation, and it maintains the equality. So I'm going to do that. Let's do that here. I'm going to take the natural log of the left side. Natural log of y is just natural log of y. And then I'm going to take the natural log of the right side. Now, the right side is all of that stuff, right? I get to cheat. Okay, so from here to here, what I'm doing here is I'm just going to call it log diff. Okay, I'm doing a logarithmic differentiation. I am applying the log to both sides. Now, the thing you need to ask yourself is, what would make you do that, right? Well, it's that you looked at the function, you said, I don't want to do this. Like, I see that I have division, right? And because I have division, if it were a log, you could split it into two logs. And then you have a bunch of products, right? You have a bunch of products in here, a bunch of multiplications. And you know that if there was a log involved, products can be split apart as well. And you see a bunch of powers, 5, 3, 8, 4. This x minus 8 to the square root is the same as to the half. So you have a bunch of things to powers. And you know if this were logs, you could bring the powers out front, right? So that's the thing that's going to make you say, I'm going to try logarithmic differentiation. All right. Okay, so I've taken the log on both sides. All right, now what we want to do is expand this out now. Okay, we're going to leave the left side as natural log y equals, and now on the right side we have a fraction, right? We have a fraction inside of a log. And now I can use this, right? So I have the blue is on the bottom, the yellow is on the top. So I'm going to split this into two logs. This will become natural log. Okay, the top log is going to have everything in yellow. Minus the bottom, the second log will have everything in the bottom. So x plus 2 to the 4th. And I'm going to rewrite the x minus 8, the square root of x minus 8 is x minus 8 to the half. Is that all right? Have I taken a derivative? No. All I've done is taken the log of both sides, and now I'm just algebraically manipulating this. Stop me if you have any questions. I have multiplication here. Do you see I have multiplication? I'm going to put black dots where I have multiplication. Anytime you have multiplications inside of a log, you can turn it into addition. That's this first property, right? So if I have two things being multiplied, it turns into two logs. What if I had three things being multiplied? What do you think?
It'll turn into 3 logs.
3 logs, right? If I had 4 things being multiplied, it'd be 4 logs added together. So watch what I do now. Natural log of y on the left side equals, okay, everything you see here in purple is going to be split using that first property into 3 logs because I have 3 things being multiplied. So I have natural log, no. I have natural log of x to the 5th plus natural log of x plus 4 to the 3rd plus natural log of x minus 5 to the 8th. Okay, that is what the purple one has turned into. 3 logs separated by addition. And then the second log over here in brown, that kind of look brown to you? I don't know. Brown. That is going to be split into how many logs?
Two logs.
Just 2, right? With what operation between them, right? Well, when we have multiplication inside of a log, we write the 2 logs with addition between them, right? Addition between them. However, this minus sign will actually act on whatever this thing in brown becomes. The minus sign must actually act on everything. So watch the way I do this. I'm going to go minus, and then in brackets, you could use parentheses if you want. I'm just using brackets to like exaggerate the fact that that negative is going to need to distribute through to the brown part, which becomes natural log of x plus 2 to the 4th plus natural log of x minus 8 to the half. You see what I mean? How that minus is going to act on both of these because it turns into 2 terms. I have to sneeze. Okay. Questions? The brown became those. Have not taken a derivative yet, right? This is all just algebraic manipulation. Anywhere I have a power, the power can come out. Natural log y equals, okay, this 5 is going to drop. 5 natural log of just x plus, okay, that 3 is going to drop. 3 natural log of x plus 4. And then plus this 8 is going to drop out front. Natural log of x minus 5. Now over here, the same thing's going to happen, right? 4 is going to drop out, half's going to drop out, and I'm going to distribute the minus now. So it's going to become minus 4 natural log of x plus 2, and then minus a half of natural log of x minus 8. Starting to look better. Question. Can I take this natural log of x plus 4? Can I take that question and turn it into natural log of x plus natural log of 4? What do you think? I'm seeing heads shaking no here. No, we can't. That's not the way logs work. The only way you can split a log into 2 logs is if you have multiplication in them, right? Inside the log, you have to have multiplication. Then you can split it. If you have, let's say, log base a of x plus y, this does not equal log base a of x plus log base a of y. It is not, does not, okay? In fact, there is no way to split it apart. There's no algebraic thing you can do. So we have to just leave it as is. It's not going to cause a problem because we can take the derivative of that. That's not an issue. Okay, we can take derivative of this. I'm going to lose all that. Any questions? Are y'all ready to do a derivative now? I think we've cleaned this up as good as we're going to get it. We've got, let's see, 1, 2, 3, 4. We have 5 terms. We can differentiate each one by one. The constants will come for the ride. The logs will become 1 over box times the derivative of the box, 1 over box, derivative of box, 1 over box. And we just kind of play that game the whole way, right? But there's a problem. We want to know what y prime is, right? And we no longer have y, do we? We don't have y equals this. We have natural log of y equals this. So what I have to do is the next step. After we cleaned it up, we are going to differentiate implicitly with respect to x, which means we're going to differentiate both sides of the equation, treating x as the independent variable. We've done this before. We've done this before with related rates and things like that. So here it comes. I'm going to take that. I'm going to do the derivative with respect to x on both sides, right? So when you take the derivative with respect to x on the left side, this is the most critical one. You have to apply the chain rule. What is the derivative of natural log of y? Y is the box, right? Y is the box. So the derivative of natural log of y would be 1 over y, okay, times now the derivative of the y with respect to x.
dy dx.
Dy dx, right? Dy dx. This will become dy dx. Now, I'm not going to write dy dx. Instead, I'm going to write y prime, okay, instead of dy dx, because y prime means dy dx. They mean the same thing. When you do logarithmic differentiation, like what I'm doing right now, you will have to take derivative of the left-hand side, and it will always be 1 over y prime, always, because that's always the derivative of natural log of y. So your left side is always going to turn into 1 over y times y prime. And the good thing about this is that the thing we're trying to solve for is here now, right? Here it is. But we also have this 1 over y, which we'll deal with in a minute. Equals. Now, on the right-hand side, everything in there has x's in it. So when we differentiate with respect to x, it's just our traditional derivative, the way we've been doing it for, since the beginning. So I bring the 5 for the ride, times derivative of natural log of x is just 1 over x. Plus I bring 3 for the ride, times, okay, here it's x plus 4, so that's what's in the box, 1 over x plus 4. And the derivative of x plus 4 is just 1. So technically I have times 1 out here, but I don't need to write it. Plus 8 times 1 over x minus 5. And then the derivative of x minus 5 is 1 again, so I don't need that out here. Minus 4 times 1 over x plus 2. And again, the derivative of x plus 2 is 1, so I don't need anything on the side. And then minus 1/2. And then times 1 over x minus 8. And finally, derivative of x minus 8 is 1, so I don't need anything outside here. We're almost there. We want to know what y prime is, right? What's y prime? So we need to get y prime by itself. So y prime will be equal to everything we just got, but I need to get rid of this 1 over y on this side. So what I'm doing here is I'm going to multiply this side by y and this side by y. So it goes away on the left. That's how I get y prime. But here I still have all of this times y, don't I? Last step. This step is just silly. Watch. What's y? Because remember, we want the answer y prime is equal to all this in red times y. But what's y? Oh, that's what y is, right? That's what y is. So I need to take this, the original function, and I need to slap it to the outside of this. Let me make it a little smaller. That's my answer. Weird, huh?
Very.
Yeah. But it's very powerful too. Let's do another example. Okay, let's do another one. I'm going to pull this one out of the book just to show you kind of the variation. So this one says y equals e to the negative x cosine squared x over x squared plus x plus 1. Find y prime. Now, I could just do a quotient rule here, right? I could just do a quotient rule. It would be a little messy though. Let's try logarithmic differentiation. So I take the log on the left side. I take the log on the right side. I have a fraction, yellow over blue, inside of a log. That can split up, can't it? Right? That can split up into two logs. Natural log of y equals, it'll be natural log of e to the negative x times cosine squared x, and then minus natural log of x squared plus x plus 1. I have a product here, so I can split that into two logs with addition. Natural log of e to the negative x plus natural log of cosine squared x. And then over here, can I split this one up? Can I split that into 3 logs?
No.
No, right? Those are pluses, right? You can't do anything with this. So I've got to leave this one alone. But really, look, when I'm looking at this, I'm not intimidated by this, because if I treat the x squared plus x plus 1 as my box, 1 over the box is easy. The derivative of the box is also pretty easy, 2x plus 1. So this is not going to be a problem, right? When I take its derivative, right? Yeah.
Mhm.
Okay. All right, what next? Ooh, there's something subtle. Before we do anything else, there's something subtle here on this first one. Natural log of e to the negative x. Natural log of e to the negative x. What is that equal to? There's a property here,
E over X.
e over x. So, okay, so aren't natural log and e inverse functions of one another? Aren't they inverse functions? Isn't that the whole idea? Is that if you give me e to the, if you just had e here, right? E to the negative x, then the natural log, if you did natural log of that, it would undo it. It would get rid of it. So in other words, when you put natural log and e together, they kill each other off, and this just falls out and becomes your answer. There's actually a property. Natural log of e to the, let's say box is equal to the box, right? That again is a property from college algebra. It's in our notes. If you need to go back and look, it's in here, right here. E to the natural log of x is x, but so is natural log of e to the x. It also is x. So that means this first part just becomes negative x. I have not taken a derivative. I have not taken a derivative. I'm still just doing algebra. Plus, now watch what I do here. Check this out. Do y'all know what I did? Where'd that 2 come from?
This.
Right, it's cosine squared, right? This right here really means cosine of x squared. So I use that property that I can pull the 2 out front. And that just gave me a cosine in there. I like this. I think I'm ready for a derivative. What is the derivative of the left-hand side? always going to be in this.
1 over
Y.
y. dy dx.
dy dx, or just, I'm going to put y prime, right? Every time you do logarithmic differentiation, the derivative of the left side is 1 over y prime. And then on the right, man, this is a pretty nice derivative. Derivative of negative x is -1, plus 2 comes for the ride. Okay, I've got to do natural log, a derivative of natural log of something. So first I do 1 over the cosine x, chain rule, times now the derivative of cosine, which is negative sine of x. But I'm done with this now. And then I have minus, and now I'm ready to take this derivative, so I just do 1 over whatever's inside times the derivative of what was inside, which is 2x plus 1. Questions? Sine over cosine, isn't that tangent?
Yes.
I can bring that negative out here and make that a -2. And then sine over cosine is tangent. And then over here, minus, I'm going to write this as 2x plus 1 over x squared plus x plus 1. Why did I put this whole thing in parentheses just now? Why did I take all this, clean it up, put it in parentheses? Why did I do that?
So you can multiply by y.
Because I'm going to multiply both sides by y, which again, you will do that every time you do logarithmic differentiation. You will have to multiply by y at the end. All right, so just pay attention to that. That's how I got rid of this 1 over y on the left side. I multiply both sides by y. But what is y? We have to go back up to the beginning. What's y? It's this, right? This is y. So my final answer will be this times this. Now, I always have students who will be like, you know what, I like it, great, thanks for showing that to us, but you know what, I'll stick to the quotient rule. You know, I'll stick to doing it the hard way. And if you want to be stubborn about it, you can be stubborn about it. Good luck with that though, because there's so many places you can make mistakes. I'm now going to show you an example where you have no choice. Okay, you have no choice but logarithmic differentiation. All right, it's not a matter of, you know, how bad do you want to torture yourself. It's a matter of there is no other way. All right, so this is a whole new category of functions you've never seen before. All right, here we go. So check this function out. It's going to look simple. Y equals x to the x. Find y prime. I need to blow my nose. I'll be right back. Think about this for a minute. Think about, if I ask you to take that derivative, think about what you would try and do. All right? Be right back. Okay. It's a little weird, right? Because we do have some rules for taking derivatives that might look like they might work. Like we have the power rule. This was that first rule that I gave you that you really liked, where if you had x to a power, you just bring the power down, subtract 1 from the power, right? So maybe you're sitting there thinking, oh, okay, well, you know, the derivative of this would just be x times x to the x minus 1. So do you see what that person did? They brought the x out front, and then they subtracted 1 from the power. That makes sense. Okay, I understand what they've done. Is it right? Maybe. Or maybe this. Maybe they use the second rule where they say they have something to the x, and they say, all right, well, then I have just itself, right, times natural log, what would it be? Natural log of what? Natural log of x, because the base is x, right? Do y'all see how I've got two different answers here. One of them is using the first rule. The second one is using this rule, right? You see that? Well, which one is right? What do you think? Neither one. They're both wrong, okay? And that's because these rules have to follow this pattern. And the first rule, you have to have the variable on the bottom, and it must be a number up top. X squared, x cubed, x to the 5th, x to the 1/2. Then you can use this rule. This rule only works if your variable is in the exponent and your base is a number. It has to be a number. 3 to the x, 5 to the x, e to the x, 10 to the x. This is a special scenario where we've got the variable both in the base and in the exponent. Do you see that? I'm going to say it again. This is a function where we have the variable in the base and the exponent at the same time. We have not seen anything like this. Would y'all like to see the graph of this? Because I know you've never studied this function before, because in college algebra, we don't study that type of function. Or in pre-cal, we don't. So let's see what Desmos does with it. Y equals x raised to the x. Whoa. What the hell? Hold on, it took the graph away. What did it do? It was there, now it's gone. What happened? The computer was thinking, it didn't know how to handle it, and then it finally said, you know what, I better not try and graph anything over there. So this is the graph. Do y'all see we do have a function? We do have a function. And I mean, it's nice, it's continuous. You can draw it without picking up your pencil, it looks like. And it looks like you've got tangent lines, right? I can go to some point and ask you for the slope of the tangent line, right? But how do we do it? How do we find the derivative then? How do we find the slope of the tangent line? Well, logarithmic differentiation is how we do it, right? So none of those work. What we need to do this is logarithmic differentiation. And we're just going to follow the same steps we just had. So what was the first step for logarithmic differentiation?
Y
Log
prime.
Log on both
Log of
sides,
x.
right? Log on both sides. So we take the log on the left, we take the log on the right. Now, do you remember that property of logs that said this? If you had log of x to the r can come down, natural log x. Remember that property? This property actually does work even if r is a variable. So even if this was x to the cosine x, it doesn't matter. No matter what this is, this can come out in front. Which is great news, because now I can bring this x out in front here. And now I have this. Natural log y equals x times the natural log x. Do you see that I've now pulled that x out of the power, right? I've pulled it out of the power. And what that's going to allow me to do now is take the derivative now. And it's become a product instead of a something with a variable in both the base and the exponent. And I can do a product rule all day long. So that's what I'm doing. So let's do the derivative now of the left is 1 over y prime. And the derivative of the right is natural log x plus 1. Why is the derivative of this natural log of x plus 1? When you take derivative of that, you get 1 times natural log x plus 1 over x times x, right? That's your product rule on this. Derivative of the first one times the second, so 1 times natural log x, plus derivative of natural log of x, which is 1 over x, times the first one x. These x's cancel, you get a 1. It's just natural log x. One more step. Multiply both sides by y, right? Multiply both sides by y. So I'm going to multiply the right-hand side by y, but what was y? What was y?
X to the X.
X to the x, so I'm multiplying by x to the x. That's the derivative. Let's see if I normally don't show this to my students, but let's see if this makes sense to you. In general, okay, in general, let's say you have y is equal to, and let's say the base you have some function of x, but then you're going to raise that to some other function of x. So like in the example I just did for you, y equals x to the x. The base was just the x function, and the exponent was just the x function. But both of these are functions of x, right? They are functions of x. What we do in order to take the derivative of this, right, to find y prime, what we do is we do the natural log on both sides. And that allows me to do what on the right-hand side? What can I do now over here? Because I have a log. What can I do?
Using the gx to the front.
Bring the gx to the front. So that means this will be a natural log of y equals g of x times natural log of the f of x. And then now do you see that you can take the derivative of this because you're guaranteed you're going to have a product here and you're going to be able to do a product rule? So I guess all I want you to see here is this. If you ever see a function of x raised to a function of x, you're going to use the logarithmic differentiation. It's going to work each time. Let's do another one. Okay, let's do a specific example. This will be our last example. Let's do y equals x to the cosine x. Try that one on your own and give you a minute or two to do it. While you're doing it, I'm going to graph it. Really cool graph. Isn't that a cool graph? What we're trying to do is see if we can come up with a formula that would allow us to find the slope of the tangent line at any point on this curve, right? That's what we're doing. let me know when you're done. Just click yes when you're done. About half of you were done. What do you think? Log on both sides. Pop the cosine X out. Differentiate 1 over y prime. Product rule. Derivative of cosine of X and negative sine X times the second one plus derivative of natural log of X 1 over X times the first one. Okay, once I've got that, now just put in parentheses, multiply both sides by y. Y was X to the cosine X. There it is. Questions? Cool graph. Look, I could ask you this question. Find equation of the tangent line at 0, 0. That's something I could ask you now, right? I give you this, and I say, hey, everyone, find me the equation of the tangent line at that point. So the first thing you'd have to do is find the derivative, wouldn't you? Find the derivative first. Okay, you find the derivative, here it is. And now what you want to do is you want to plug in x equals 0 into this derivative, and that will give you the slope of the tangent line at that point. Let's try it. Let's plug 0 in here. It's not as bad as it looks. It's negative sine of 0 times natural, oh wait, shit, hold on. 1. Oh, you know what? It's not defined at 0. We can't do it. Cosine of 1. Nah, we're gonna have to leave it alone. Sorry, I couldn't ask you at that point. I apologize. I could give you another point, but it would be a hard point. I could give you 1 cos. Yeah, no, let's not do it. It's too difficult. That's beyond what I'm trying to get you to see. But theoretically, right? Theoretically now, if you have a point on that curve, then you could find the equation of tangent line by just plugging in that value into this. I was trying to pick a point that'd be nice, but there are no nice points. I don't see any nice points here on this curve. Why is it saying that 0, 0 is on that curve? That's weird. All right, I'm done. 3.3 is done. We're moving on. You should do all that homework now for that section 3.3. I would, you know what did I tell y'all to do last time on this 3.3? What did I tell y'all to do?
1 through 39 odds, I believe.
1 through 39 odd. Okay. I would say to not mess with this assignment. Just continue. Your total assignment for this would be for you to try and do like 1 through 1 through 39 odd, okay, which you already did. And then now what I would try is like 41, 41, 43, and then 51 through 58. But do all of the problems 51 through 58. I've done one of them for you already. I already did number 52 in class. So the 51 through 58 has to do with logarithmic differentiation, which is what we've done today. All right, we are not going to cover 3.5. We are not going to cover it. Now, don't panic. That'll probably be the first thing you do in Cal 2. When you get into Cal 2, they're going to go right to 3.5. Make sure you know what the inverse trig functions are and what their derivatives are. Okay, so we're not going to cover it. So none of this, don't worry about it. We are moving on. Normally, if I have time, I'll squeeze it in, but we don't have time. All right, y'all ready? 3.7, last section out of chapter 3, and then we move on to chapter 4. 3.7. Let me see what I have in my notes on 3.7. Yeah. Y'all ready? I need you to kind of clear your minds a little bit right now. All right, just kind of take a step back. We are now going to revisit a topic covered earlier in this course, limits, right? Isn't that the way where we started the course, with limits? We're about to go back and do limits again. But we're going to learn about this new rule called L'Hopital's rule, which you're going to love for a little while, and then you're going to realize it can get complicated, but you're still going to love this rule, okay? L'Hopital, it looks like La Hospital, but it's L'Hopital. It's named after a mathematician, okay? L'Hopital's rule. So this is the way I want to kind of introduce this idea. If you go back and look at what we've learned how to do in this class in terms of limits, remember this page? Remember this thing right here? Where we had, oh, if you ever see 0 over 0, you need to do some algebra. See infinity over infinity, some sort of algebra, some sort of trick. 0 times infinity, infinity minus infinity, right? All these different things. If we had 0 over fixed, fixed over infinity, fixed over 0, all these different scenarios, right? You've now forgotten about this, right? No? What we're going to do now is revisit this, and we're going to really be focusing a lot of attention today on these scenarios right here in green, okay? We're going to really be focusing on those. But we've got to start out, let's just start out, baby steps first. So I want to go back and do a limit that you're familiar with. That if I gave it to you, you wouldn't be like, oh God, that sucks. What is the limit as x approaches 2 of x squared minus 4 over x minus 2? So let's see. Remember how to do this? When you do a limit, first thing you do is you try and plug in the value that you're approaching. So here we're approaching 2, right? So if I try and just plug in 2 on top, we get 2 squared is 4, 4 minus 4 is 0. So the top is headed to 0. And then the bottom, 2 minus 2 is also headed to 0. And this is where we'd say this is bad. We need some sort of algebra, or we need some sort of trick, right? And what would the algebra be here? If we were to do this problem.
Take the numerator and separate into 2.
Yeah, we would factor the top, right? That's difference of squares. We do x plus 2, x minus 2, and then over x minus 2. We would cancel these two factors. And then we would let x approach 2, and 2 plus 2 would give us 4. Right? That's how we would do that problem. I'm here to tell you there's an easier way now, okay? And it's based upon this thing called L'Hopital's rule. So here's the way the rule works. I'm going to give you the actual rule in a second, but I'm just going to do this problem again using the rule. Okay, so rewrite the problem. And the first thing we do is we recognize that we do get from this 0 over 0, right? 0 over 0. But you know how we used to say this is bad, we need some algebra? Now what we're going to say is, oh shit, this is good. We can use L'Hopital's rule. So what is the rule? Again, I'll give you the rule like formally in a second, but I'm just going to tell you what it is, right? L'Hopital's rule says, is everyone getting calls from the school saying there was a fire drill? That's what I'm getting here. L'Hopital's rule is says that if you have 0 over 0, okay, you have to have 0 over 0. If you get 0 over 0 in a limit, then what you can do, oh man, this is so awesome. What you can do is do the limit as x approaches 2, but instead of doing x squared minus 4 over x minus 2, take the derivative of the top and bottom separately. So what's the derivative of the top? Just the top.
2x.
Don't do quotient rule, just the top.
2x.
2x. Okay, what's the derivative of the bottom?
1.
1. Okay. Now try 2 again. 2 goes in. What do you get on top? 4 on the bottom. 1. What's your answer? 4.
4.
Same answer. Didn't require any algebra. I just had to take derivative of top and bottom. That's pretty nice, huh? That's pretty nice. Let's do another one. I'm not going to give you the rule yet. Okay. How about this one? Limit x approaches 0 of sine of 5x over sine of 3x. Ooh, do you remember how we did these? Look, if we try and plug 0 in, sine of 0 is 0, so we get 0 on top, and sine of 0 is 0, we get 0 on the bottom. Do you remember how we did these? This was like a really weird problem where we would like rip it apart, and we'd say, boy, I really wish I had a 5x down there, and oh, I'm just going to make a 5x appear, and then, right, remember all that? It was like, what? Okay, do you have 0 over 0? Yes. Can you use L'Hopital's rule then? Yes. So what I'm going to do is say equals limit x approaches 0. Now I'm going to take the derivative of the top and bottom separately. No quotient rule. Don't do a quotient rule. Just the derivative of top and bottom separately. What is the derivative of the top? Careful.
Cosine.
Cosine of 5x
Or 5.
times 5. Chain rule, right? Times 5. Over, now the derivative of the bottom.
Cosine
Cosine
3x 3.
times 3. Okay. Now try and plug 0 in. Now try it. If you plug 0 in here, you get 5 times 0, that's 0. What's cosine of 0?
1.
Right? 1. And then same thing down here, 3 times 0 is 0, cosine of 0 is 1. So what you're getting here is 1 times 5 on top and 1 times 3 on bottom, which means your answer is 5/3, which is what you would have gotten had you done all that other stuff, right, from before. Now look, I need to somehow tell you I'm using L'Hopital's rule. Okay, so like when you look at this and I went from here to here, you know I use L'Hopital's rule because I told you I did it. And from here to here, I told you I did it. But we need some sort of mathematical notation to let whoever's looking at our work know that we just use L'Hopital's rule. So the standard notation for it is this. You put an H above the equal sign, and sometimes you circle it. H above that and circle it. Now, I personally, I don't know why, when I was learning it, I did an L and circled it because L'Hopital made more sense to put the L and not the H. I don't care what you do, use an L, use an H, somehow let people know that you're using the rule, and that's the notation that lets you know, okay? If you don't do anything, then you're trying to convince me that these two are the same things, and they aren't the same things. They are by the rule, they're the same things, but algebraically, they're not. Can we do another one? Thank you. We will. How about this one? Limit x goes to infinity of x, let's go 4x squared plus 3x minus 1 over x squared plus x plus 1. Where's x going here in this limit? Not 0, right? X is going to infinity. So where does the numerator go?
Infinity.
Infinity, right? Where does the denominator go?
Infinity.
Infinity as well. Everyone okay with that? I mean, we've done those in the past. Everyone see we have infinity over infinity? Normally, when we would have this, let's see if anyone remembers this. When we had infinity over infinity, what we did was we tried to look at the highest power of x in the denominator. And then we come in here and we would do like a 1 over x squared here, 1 over x squared here, right? And then distribute it through and try and make things work out for us. Remember all that stuff we did before? Guess what? Guess what? L'Hopital's rule works when you have infinity over infinity as well. It works when you have 0 over 0, and it works when you have infinity over infinity. So I'm going to use it. I'm going to say L'Hopital. L'Hopital. I think in my homework solution videos, I sing L'Hopital a little bit. You'll see. Because it's such a great rule. So here we go. Take derivative of the top and bottom separately and then run the limit again. Okay, what's the derivative of the top? Oh my gosh, that's enough.
8x plus 3.
Yes, 8x plus 3. Everyone got that? 8x plus 3, right? No quotient rule. L'Hopital doesn't do quotient. Okay, L'Hopital just does top and bottom. And then the derivative of the bottom, 2x.
2x plus 3 plus 1.
1, right? Okay, now run your limit again. Run the limit again. What happens when x goes to infinity on top?
Goes to infinity.
Goes to infinity on the bottom.
And then it goes to infinity at the bottom.
Still infinity, right? We still get infinity over infinity. Well, guess what? You can do it again. You can do L'Hopital's rule again. As long as you have 0 over 0 or infinity over infinity, you can keep going and going and going. So now, again, by L'Hopital's rule, L'Hopital, derivative of the top,
8.
8, derivative of bottom,
2.
2. Okay, you have no more x's, right? So now it doesn't matter what x is going to. Your answer is 4. This is annoying. I'm gonna silence my phone now. Wasn't that nice? So let's look at let's look at the formal L'Hopital's rule. All right. Here it is. Okay, so L'Hopital's rule. Suppose you have two functions that are both differentiable. Let's not get too bogged down on this. If you're taking a limit and you get 0 over 0, okay, then all you have to do is take the derivative of the top and bottom and try that limit and see if it works out. If you get infinity over infinity, and it doesn't even matter if you have positive or negative infinity on top and bottom, but if you have infinity in both, right, positive or negative, then all you have to do is run L'Hopital's rule, take derivative of top and bottom, and then see if that limit works. Okay, it only works for infinity over infinity or 0 over 0. That's it. That's the only time you can use L'Hopital. Okay. Shall we do one more? Let's do one more, and then I have a question for everyone. All right, how about this one? Limit x goes to 0 of sine x over x. Does anyone recognize that? And can someone tell me the answer quickly? I see Ash saying 1. This is a limit I told y'all to memorize. Way in the beginning of class, I said, look, this is a limit you need to know, This is the one that was like sine junk over junk. Remember that sine junk over junk? As long as the junk goes to 0, this limit's 1. I told you that this was 1, but I told you that there was not an easy way for me to show it to you yet. But later on, I would show you that it's 1. And now it's time to show you it's 1. Because if we do this limit, sine of 0 is 0. We get 0 on top and we get 0 on the bottom, right? So L'Hopital's in play. So I take the derivative of the top and bottom and run the limit again. Derivative of the top, cosine x, derivative of the bottom, 1. Now if x goes to 0, cosine of 0 is 1, so you just get 1 over 1, that's 1. There's another way to prove this without L'Hopital. I think I told y'all the only way I could do it is if it came to my office hours, and it would require some geometry and squeeze theorem and some other stuff. And it's complicated. It's actually really nice, but L'Hopital, boom, it's like that. It's like when you don't have to think about it. It's simple. What do y'all think? L'Hopital pretty cool, right? I always get students that ask this question. Why not just like give us this in the beginning? Right? Why not just give us L'Hopital in the beginning? Why make us suffer through all that algebra? Why not just give us this in the beginning? Why do you think we don't give this to you in the beginning? Just torture you or what?
I feel like it's
What's that? I heard a couple of things.
I was saying like maybe to recode the algebra.
Okay, so yeah, I mean, it really forced us to understand the algebra, right? Yeah, but there is a reason why. There is a reason why.
I think it's so we can understand like how we get somewhere, like where, like how it starts and what you can understand the math in between.
Yeah, I mean, the limit, doing it all by hand algebraically is essential in understanding, how to manipulate things. But there is a real reason why we didn't. I mean, there's a real reason. It wasn't just like to force you to be better math students. There's a reason why.
Maybe it's because L'Hopital's rule doesn't work on every limit equation.
It does not work on everyone. That is correct. It does not work. Sometimes when you do this, when you do L'Hopital, it gets more complicated, right? So let's think about the evolution of this class. What did we start this class with? Limits, right? That's what we started with, right? We did all these limits, and then from there, after that, what did we learn about?
Derivative.
The derivative, right? We said, hey, there's this one particular limit that's very special, and it was f prime of x, and this is a limit as h goes to 0, f of x plus h minus f of x, right? All over h. And we suffered through that for a while. And then after that, we gave you all the shortcuts, right? Shortcuts. So we gave you power rule, product rule, quotient rule, chain rule, right? And that, we went places with that. And here's where we are now, right? And now we're coming back and I'm saying, hey, let's do some limits again using L'Hopital's rule. So why didn't we give you this in the beginning?
We didn't know how to do derivatives.
Yeah. So what if I would have walked into class and I would have said, hey, everyone, we're going to do this limit. So what we're going to do is take derivative of the top and bottom. You would have been like, what the hell is a derivative, right? Like you wouldn't have known what I'm talking about. And especially like on a problem like this one, where this one here, right there, right? Sine 5x, like how am I supposed to, like when you have no idea what a derivative is, how are you supposed to understand how sine 5x somehow turns into cosine 5x times 5, right? Like what happened? It seems like I'm doing magic. So the reason we don't do L'Hopital in the beginning is because you don't know what a derivative is yet. But now it's kind of, to me, it's kind of amazing when you really think about it, because it's like we learn how to do limits. And then from that, we kind of birth this idea of a derivative. And then we find out later that, we can actually use that idea of the derivative to come back and do limits. So it's like we built a tool from the limit that becomes a tool that we can use to do more limits. It's really actually kind of nice. Math works like that sometimes. We go down these roads, we don't even know what the hell we're trying to do. We just do it, and then we say, oh my gosh, at the end we say, oh, we can use this over here. Like, we don't even realize that we weren't even trying for that. And we realize that that can help us do something else. Okay. Let's try one that will make you not just absolutely fall in love with L'Hopital. I don't want you to be like, oh, this is the end all be all, right? Like, this is it. This is the what do they call that? I don't even know what I'm trying to say. Limit x goes 0. How about this? X cosine x over sine x. I'm making this problem up. It might work, but I have a feeling it's not. Let's see what happens. All right, first thing we do is we just figure out what happens when you plug in 0, right? Just plug in 0. On the top, you get 0. On the bottom, you get 0. All right, so L'Hopital's in play. Here it comes. L'Hopital. L'Hopital. All right, so I have to take derivative of the top, which is a product rule. Don't, right? See that? I have a product rule. Okay, that's going to be cosine x minus x sine x all over the derivative of the bottom, which is cosine x. I did that product rule like kind of quickly in my head, right? I did derivative of x is 1 times cosine, and then derivative of cosine is negative sine times the first one, brought the negative out. Let x go to 0. I think we're good here. I think this is going to work, right? If x goes 0, cosine of 0 is 1. Minus, okay, 0 times 0 is 0. And then all over cosine of 0, which is 1. So the answer is 1. Okay, so that one wasn't bad. All right, here's one that's bad. All right, I know this one's not going to be good. Limit x goes to infinity, x plus 1 over square root of x squared plus x. Okay, that one won't be good. What happens is x goes to infinity. Infinity on top, infinity on the bottom, right? So here you come with your L'Hopital machete, right? Like ready to go after it, right? Here you go, you're all happy. L'Hopital, you're singing in the shower, right? The derivative of the top isn't fine, right? Derivative top is 1. You're like, oh my gosh, this is beautiful. And then you go to take derivative of the bottom. And that's a chain rule, right? You've got to do derivative of the square root of something, which is 1 over 2 times the square root of that something, right? Times the derivative of what's in there, which is 2x plus 1. Now we have to figure out what that's doing, right? We need to figure out what this is doing. This is going to need to be cleaned up before I can conclude anything. So I have 1 over. So I'm going to slide this 2x plus 1 on top here. I have 2x plus 1 over 2 times the square root of x squared plus x. You understand? Now, 1 divided by a fraction means I can rewrite it as a reciprocal, right? So I can rewrite this as limit x goes to infinity of 2 root x squared plus x all over the 2x plus 1. Just flipped it. And now when I run the limit again, I get infinity over infinity again. And so you have to do L'Hopital again. And what's going to happen is every time you do it, you're going to continue to get infinity over infinity, infinity over infinity, infinity over infinity, infinity over infinity. It's never going to get better. I'm going to stop here. You're just going to have to trust that it keeps getting you in a place that you don't know the answer. So the way to go about this problem is to come out here and say, oh, 1 over x out here, 1 over x out here, push the 1 over x inside to kill off the x squared. So you would want to use the old method. Now, would you want to try L'Hopital first? Probably, but then pretty soon after you do it, you want to be like, okay, I got to go back and do the other way. So L'Hopital is like a tool. We want to know how to, we want to know it's there. We want to know how to use it, but we don't want to become dependent on it because it won't always work. It works a lot of the time, but not always. All right. So 0 over 0, infinity over infinity. We're happy, yes? I'm going to give you 2 to try on your own. Limit. Let's use a different variable. T goes to sorry, I'm thinking. T goes to 0. E to the T minus 1 over T squared. Try that one. And then try limit x goes to infinity of x to the 4th over e to the x. I will give you a few minutes. We only have 6 minutes, so let's try and go like maybe 4 minutes, see how far you can get on these. Let me know if you're done. On the first one I gave you, I want to approach 0 from the right. I need to put that there for you. Be careful on that one. All right, I only have like 2 minutes left, so I'm just gonna run through these real quick with you. The homework for this section 3.7, what you can do right now, try 1 through 21 odd, okay, for this section 3.7. On the first one, first thing you do is let t go to 0. E to the 0 is 1. 1 minus 1 is 0, so you get 0 on top. 0 squared is 0, so you get 0 over 0. So you're like, okay, I'll use L'Hopital. So you do L'Hopital, you take derivative of the top. Derivative of e to the t is itself. Derivative of 1 is 0. So you get e to the t on top. Derivative of t squared is 2t. Now, careful. Run the limit again. As t goes to 0, e to the 0 is 1. And 2 times 0 is 0. So you get 1 over 0, right? 1 over 0. Can't use L'Hopital anymore because it's 1 over 0. It's not 0 over 0. It's not infinity over infinity. So now I just think about what's happening here. The top is headed to 1, which is a fixed positive number. The bottom is headed to 0. And because I'm approaching 0 from the right-hand side, it's approaching 0 through positive numbers. Anytime you have a fixed number that's positive over a number that's headed to 0 that's positive, you'll get positive infinity. How do I know that? Because we studied that back here. Fixed over 0, fixed over 0. We know that there's only these possibilities. So yes, you have to remember that stuff. On the second one, x goes to infinity. Infinity to the 4th power is infinity. E to the infinity. E to the infinity. The way you can think about e to the infinity is just thinking about the graph of e to the x, right? What happens as you go out to infinity? The graph heads up to infinity, right? So you get infinity on top, infinity on the bottom. You do L'Hopital. Take derivative of the top, you get 4x cubed. Derivative of e to the x is itself. And do you see that you get infinity over infinity again? So you try L'Hopital again. And you get infinity over infinity again. And you might think, oh, wait, this isn't going to work. But do you all see that every time you do L'Hopital, you're chipping away at the power in the numerator? It goes from 4th power, 3rd power squared down to x, 24x. And then on this last L'Hopital right here, you finally get to a number on top, 24. E to the x, every time you did derivative, it just continued e to the x. So you finally get a fixed number on top over something that's becoming infinite. And fixed over infinity goes to 0. Have fun with the homework. Have a good weekend. When do we have a test? Do we have a test sometime soon? I feel like we do. No, not for a while. All right.
Thank you.
All right. Have a great weekend. Do your homework.
Have a good weekend.
Thank
All
you.
right. Y'all take care.